and welcome back for the second day of our Python training. I have posted in the chat, and I will post it again, the link to the course materials. And if you click on that link, you'll get a web page that looks like this. And if you scroll down, you see all the lessons for our training. And then where we left off last time on Tuesday was with command line programs. So I'm going to click on command line programs and scroll to the bottom. And down here in kind of the orange color were the exercises that you were asked to do after our Tuesday training. Hopefully you had some time to take a look at these and to try to implement them in our plot precipitation climatology.py script. So I can take some brief questions. If you have questions about that, you can put them about these examples. You can put them in the chat window, and I can try to briefly answer any of those questions. If it's a longer question, we can address that during the breakout. So I'm looking to see if there's any questions in the chat window related to the exercises at the end of our training on Tuesday. Not seeing any, trying to see if there are any hands or questions, which I'm not seeing either. I see there was a question. We can always address, if you feel like it might be a long question, we can always address it during the breakout session. All right, I'm not seeing hands raised or questions. And if you wanted to get, says for the parts that say Python, I am reposting the links to the instructions again. For the parts that say Python, should we be opening a Jupyter notebook or making those changes, or should we have been able to make the changes to the Python script from the command line? So in this case, our plot precipitation climatology.py file, you should be able to edit this plot precipitation climatology.py file either in Jupyter, but not as a notebook, as a .py file, or at the command line using your favorite text editor. We're working now from this .py, which is not a Jupyter notebook. It's its own separate Python script. I see a question. Could you address the reason for if name equals main syntax? I'm not sure that I can clearly explain why it's that way. It simply is. I don't know if Damien wants to speak up and maybe explain that, or someone else wishes to kind of explain that syntax in more detail.
Yeah, the explanation, Kathy, is at the beginning of the lesson. It's kind of, the explanation is written out in detail if Elliot wants to have a read at the beginning of that lesson. It's basically a shorthand way of asking whether the script was executed at the command line. So normally you want your script to behave differently if it was imported as opposed to if it was executed at the command line. And that if name equals main is a way to effectively ask that question. You go, was this executed at the command line? If the answer is yes, do all these things with the argparse library in order to read the arguments from the command line. And so, yeah, Elliot, have a read of the top of that lesson page, and it goes through the rationale in detail.
All right, thanks, Damien. I see a question. I'm wondering why we have to use choices keyword when we can use three-letter season even without specifying choices. So the goal here for choices was to force it to require these three-letter combinations, or to give you an error if you chose a different one. So for example, suppose I chose JFM. Well, that's not one of the options, and I want it to give me an error to tell me that I have entered an invalid three-letter combination for a season. So this is forcing it to be one of these 4 season combinations. Hopefully that answers the question.
Bless you.
Here's,
Hey, Mom, sick.
maybe we can mute people who are not presenting or speaking at this time. I see a question about, could you develop a loop for the 4 seasons? You certainly could do that if you wanted.
Hey,
you can
Kathy,
do lots. There's lots. Go ahead.
I'm going to mute everyone, but you just have to unmute yourself.
All right, I should be back. Okay, I think I've seen, I don't see any more questions showing up at this time in the chat window, and hopefully if there are other questions, we can address those during the breakout. So what we're going to do from here is we're going to start with where we ended in this command line programs. And so if you look at the bottom of this of the web page, there's an example here, and you can call plot precipitation climatology.py, and you can expand that. And it shows you an example of, at the conclusion of this lesson, your plot precipitation climatology.py script should look something like the following. And so what we're going to do is we're going to start with this so that we all start from the same place going forward. So even if you didn't complete all of the exercises or had some issues, we can start with the same thing as we go forward today. So what I'm going to do next is I'm going to open my terminal window. I'm on a Mac, so that's just a simple, for me, it's just a terminal option at the bottom. And I'm going to make it larger, and I'm also going to make my font larger so everybody will be able to see it. And then I'm going to CD into our Data Carpentry lesson directory. And if you did follow the instructions exactly, then it should be on your desktop. So I started in my users directory, and then I'm going to CD to my desktop, and then CD to Data Carpentry. So now you can see I'm in my Data Carpentry directory. So everyone should CD to that Data Carpentry directory that they created on Tuesday. And you can see in that directory, there's what we previously had, our plot precipitation climatology.py. And what I'm going to do is I'm just going to move that plot precipitation climatology.py file to a one where I save it off. I don't want you to lose something if you're testing out something or playing with something. And so I'm just going to call it .save and move it out of the way. And we're going to create a new one that starts from exactly where that what we have here in the lesson. So I am a VI user, but you can open with any text editor that you like. I'm going to open a new precipitation climatology.py file. And I'm going to cut and paste from the end of the command line section from last time so that I have exactly what's here at the end. And I'm going to save that. So I'll give you all just a brief moment to have a chance to copy it for yourself if you wish, so that you have a plot precipitation climatology.py file that matches the end of where we left off with the last lesson. And just to confirm that there are no issues, I'm going to run this just to make sure there's not a problem in my copying. So I will, one thing I want to do before I try to do anything is I want to make sure I have my environment activated. So I have the environment, I'm going to use the conda activate command. And I have PyAOS -lesson. I created a separate environment for that. And so I can tell that I have this activated because it's here to the left of my prompt. It says PyAOS lesson. Some of you created a base environment instead, and to activate that one, you would say conda activate base. So we want to make sure that we're in the right environment so that our programs will run and be able to import the packages that we're using in this lesson. So now I'm going to run the plot precipitation climatology.py just to make sure everything is good. And so I'll type it, plot precipitation. I'll type it all out, but I'll encourage you to use the tab. And hopefully that will give you time to type it as well in about the same amount of time it takes me. So plot precipitation, climatology, we'll all find out what a terrible typer I am, .py. And then we have a data directory that contains this file that we want to give to our program, -cn2 underscore historical underscore R1 I1 P1 F1. A very long file name, many opportunities to mistype something, and then 2014 So I've given it the input file. So I've gone with Python, the name of the script, and the input file. And then I want to tell it which season I want to plot. And then I'm going to give it a output file, which is the name of the image I'm going to make. So precip cm2 access cm2 underscore mam.png, just to keep it short. And so we'll try running that. And it will take a minute as to process the data on my Mac, which is not terribly fast. Apparently very slow today. All right, so it's completed. And so now I'm going to, what I'm going to do is to launch a Jupyter notebook. I have to spell Jupyter properly, with an ampersand at the end so that I'll get my prompt back. So I do get my prompt back after this. And I have a Jupyter notebook, and I'm simply just using this as a way to, as like a file browser, so I can see where my image came up. So my image was created, and I can confirm that the image that I created by running my program was produced. So now that we have the same, we all should have the same program ending from the last time, and we should be able to run it and produce our precipitation climatology for a given season. We're going to go to the next lesson. And you can do that easily on the web page, just, you can't see this, easily on the web page by clicking the arrow here. And so now we're going to get to the next lesson, which is version control. So we have this working program, and we want to make sure before we add additional things and try to do additional development that we can store it somewhere safely and not, and not lose what we have as a working program. And I don't know about you, but I've had plenty of times where I had a working program and I was like, all right, great, it's working. I'm going to add something new. And I start adding new things and I make a big mess. And I can't even get back to where I had something working. So what we're going to do to help us avoid that frustration and that problem is we're going to use version control. And so what we're going to do is store this program into a version control system so we have it stored safely and we can keep track of any changes we make and go back and restore the working version if we make a big mess. And so I'll encourage you in this lesson to type along with me in terms of doing and setting up the revision control for this project. You should, hopefully, my goal is to type slowly enough and explain clearly enough that you'll have time to type it yourself. So the whole point of this version control is to avoid having to, losing things that are working, and to be able to keep track of all the different versions of our code and keep track of the changes we make. And so just as an example, I don't know about you, but this has happened to me many times. I have a file, I call it _test. Then I realize that I need to make a change and I save it as retest. And then I have and then I have not bad. And then I have use this one. And then I have to give up and start over because I've made such a big mess. And so we'll avoid that by setting up this version control. It's also helpful for collaborating with others as well. So the most common system used for version control is called Git. And you may have heard of GitHub. That's kind of a public version control repository. But what I'm going to teach you in this lesson is how to set up a local at the command line version control for your own projects. And so we're going to use this, like I said, Git is the most common one. And when you first use Git on a new computer, you have to configure a couple of things. And so the first thing we're going to have to configure is a username. And then the second thing we're going to have to configure is an email. And so if you already have a GitHub account or use Git, you'll want to use the same username and email that you typically use. If you haven't done this before, that's fine. You'll just want to think about whether you prefer to use your work email or a personal email. So anytime we want to do something with Git, the first thing we have to type is Git, and then we have to give it some sort of command that is an action. So in this case, we're going to say git config, and then typically, sometimes there's options or things we give to the command after we say git and what action to take. So in this case, we'll do --global and then user.name. And then after that, we put it in quotes and we tell it our name. So I'm going to give it my name and you should give it yours. And then you hit enter. And nothing really should happen. So it's fine. It should be perfectly okay. And then we'll configure our email. And again, if you start the commands with git, you give it an action to take. In this case, we'll give it --global and then user.email. And I do all of mine. I give mine a personal email address. And again, you can choose personal email or you can choose work email depending on what you prefer and your work's rules for such things. All right, so now we've set up this basic configuration that needed to be preset. And you can always go back and change this if you need to. But we only have to do this the one time. So we won't have to do this again for this particular for Git on this particular computer. So just double check that we're in the right location. I am in users, my username, desktop, and Data-Carpentry. So that's where we want to be when we do continue doing this. And so what we need to do first is we need to tell Git that we want this project to be stored in a Git repository. So we have to tell it by giving it the git command and an action, and that action in this case is init. So anytime we want to start a project as a Git repository, we say git init. And we get information. Git's really good about giving us information, or we can ask it for information. It gives us a lot of useful feedback to the screen when we ask it to. So in this case, it tells us it initialized an empty Git repository, and it tells me where it initialized it. So initialized it in my Data Carpentry /.git directory. So if I do an ls-f or just a plain ls, I don't see this Git directory. The reason that I don't see this Git directory is because it starts with a dot. And when I just do a plain ls, I don't see any of the subdirectories that start with a dot. So I have to tell ls to show me all of the directories, really all of them, with the -a. And so now I can see this .git subdirectory. So this is a special subdirectory that's been created by Git, and it's going to store all of the information about your repository, all of the history of your project. If you delete this directory, you're going to delete all the project's history. So if you don't want to lose your project's history, don't delete this .git directory. So now that we've initialized our Git repository, we can check to see what's going on, that everything's okay to start up with. And the command for that is, again, starts with Git, followed by some action, and that action is status. And so the status of our new Git repository is that there are a bunch of files that are untracked. And so what that means is Git doesn't know to follow or track or keep track of the changes of these files yet. And so we're going to need to tell it which files we want it to keep track of. And it does a nice job, like I said, of giving you feedback to the screen. It kind of tells you what to do. It says untracked files, use git add file to include in what will be committed. So it's telling us what to do. It's telling us which command to use, git add. So if we want to tell Git to track a file, keep track of the changes of a particular file, we use this git add command. So git add, and let's tell it to keep track of our plot precipitation climatology.py. So in this case, Git doesn't automatically give us any feedback to the screen, but we can always ask it to tell us what's happening or what's the status of our Git repository with the git status command. So by adding this file, it now knows that there's the new file exists. And so it now knows to keep track of this particular file. But it tells us a couple of other things. It tells us that the changes need to be committed. And it says no commits yet. So what happens with Git is you have to first tell it to pay attention to or to track the files with Git, a particular file with git add. And then you have to tell it, store that in the repository. So it's a two-step process. So first we git add the file, and now we need to git commit the file. Or you can actually git commit a group of files, anything that's been added. So we add things first, and then we say store those things away so that they're saved and I won't lose them. So the command for this is git commit, and then we have to say, give it some information. So we're going to tell it a message, and this is sort of a short little brief phrase that will remind us what was it we did, what changes we made when we were to our programs, our project, when we committed this. So in this case, we're going to say git commit -im. Im stands for message, to help you remember that. And then in quotes, we're going to say initial commit of precip climatology script, and then close your quotes. And now it says one file has been changed. It repeats my message to me, my little message about what I committed. And it also indicates a unique identifier associated with this commit. I'll just let you know that if you don't do the -im part, then an editor will be opened for you to force you to give it a message. So I find it easiest to remember to just give it a message on the command line. But if you forget, it will remind you. So we've now added the file and committed the file. So they're kind of both, we've done both steps that need to happen in order to save our file to the Git repository. So now we can check just to confirm the status of things with Git status. And now it knows that we have these other untracked files, but nothing is staged to be committed. So nothing has been added that hasn't been committed. So the other thing we can do is we can kind of take a look at what have we done. So I don't know about you, it happens to me all the time. I do a bunch of things. I go to a Zoom meeting, I come back, and I can't remember what did I commit, or I may come back next week to this project and I can't remember all of the things that I committed to the repository, but I can use git log to tell me what are all of the committed things I've done, what all the commits that I've made to this repository. And so we can see that we committed this particular, this last commit that it gives me my message, so I can kind of remember what it is that I was doing. It tells me who committed it. It gives the username and the email. So this is exactly the username and email that you started with when you set them up at the beginning. And it tells me exactly when it was committed. It also gives a very long 40-character, I think, unique identifier for this commit. So now we know how to add the file. We know how to commit it to the repository. We know how to take a look at what's going on with the status of our repository, and we know how to check the log to see what we've committed to this repository. So now let's see what happens if we make other changes. So I'm going to use VI, but you can use your favorite text editor, and I'll say VI plot precipitation climatology.py. So I'm going to open our precipitation climatology.py file. And I'm going to scroll down all the way down to where we have the description. So that's, if you scroll, or you can do a quick search for those of you that have the search ability. We're looking for this line here that says plot the precipitation climatology. It's the description equals. And so we're going to modify this line. And I'm going to change it to say plot the precipitation climatology for a given season. And then I'm going to save the file. And now I'm going to do a git status. So if I do git status, Git now knows that this file has been changed. But it also knows that it has not been added. It's telling me it changes not staged for commit, use git add. And then no changes added to commit. So it's telling me that I have not yet added this file, even though I've made changes to it. So it knows it's changed. That's great. It's keeping track for me. So we're going to need to add the file. But before we do that, one thing that's really good is to always double check. Again, I don't know about you, but I often forget what I was doing because I may have turned to something else and come back and I'm like, oh no, did I get all the changes I wanted to put in there before I added it? So I can do something called git diff. So again, it's that standard git thing where I type git and then some action. And if I do get this git diff command, it will tell me the differences between the version of plot precipitation climatology.py that's in my Git repository and the version that I have locally that I've just made changes to. So you can see when it does that comparison, it's giving me a minus sign. It does a nice job of syntax highlighting for me. So it says I removed this line and I added this line. And that makes sense. That's exactly what we did. So we're kind of convinced that using git diff, we can convince ourselves for sure that we did what we intended to do before we commit anything to our repository. So let's do a git commit. I'm going to say git commit small improvement to help information. So let's see what happens here. So when I do that, it's telling me the changes were not staged for commit, no changes added. So what went wrong? Something went wrong. I didn't do it quite right. What happened is that I forgot the add step. So remember, when you make a change to a file, you need to add it to the repository. So you need to do the git add, or you need to add it to the staging area, git add, and then you need to tell it to commit it to the repository. I jumped straight to the commit and I forgot to do the add. But the nice thing is that git kind of tells me that it didn't really, it kind of tells me that I didn't do that. So let's git add plot precipitation climatology.py. And now let's commit it. So we get both steps in there in the right order. And I'm just repeating the same exact commit message I had before, which is small improvement to help information. So now it's telling me I changed the file. And you can say git status, and just confirm that everything's been done. So now we have nothing waiting for us. We have nothing that's been modified that hasn't been added or committed. So just kind of a reminder, because I found it when I first started using Git, I would tend to forget that there was this two-step process. And so this is a little bit of a picture that helps us remember what's happening. Is that first we make a change to a file, and we have to add it. And when we add a change we add this to, we do the git add, we're putting it in a staging area. And actually I can make changes to multiple files and put them in the staging area. Usually you want to do that around something that's sort of a common purpose. So maybe I'm making changes to the citations in my LaTeX file. And so I may do that in multiple places or multiple files. Then I will, I can put multiple files in the staging area, and then I have to commit it to go to the repository and to store it there permanently. So again, this two-stage process where I put things in the staging area and then I put things in the repository. And so it's git add and git commit. So we're going to walk through that process one more time to sort of help reinforce it. So now we're going to open our plot climatology, plot precipitation climatology.py file. And we're going to make a change to it. And the change we're going to make is that there's sort of a style guide around the order in which you should do imports in Python. And that order is to first you give standard Python libraries, then other external packages, and then any modules of your own, and then to put a space between them. So what that means in the case of our program is this argparse is a standard program Python library, so it should really go at the beginning. So what I'm going to do, and then have a space between it and the next set. So I'm going to put import argparse at the beginning and delete the one that's at the end. So I've just made this change to move argparse up to the top and put a space between it and the next set of libraries. And so I'm going to save. And so I'm going to do a quick git status. And that reminds me that the file's been modified, but it hasn't been staged and it hasn't been committed. And then I can do a git diff, and I can see that I can see the change that I made. So I've removed argparse from here, and I've added import argparse up here, and I've added an extra line, blank line. So before we do this, I want you to think, what are the next steps? It's a two-step process. So there's two git commands. The first one is git add. The second one is git commit. So that's what we're going to do. So git add plot precipitation climatology.py, and then git commit, and then give it the commit message. And I'll say ordered imports according to PEP8, which is the style guide that tells us the order we should be using for the imports. And so now it tells me I've changed one file. We can check our status again. I do this a lot. I type it many times just to confirm that everything's going as planned. And so now we can see that we don't have any sign of a file that's been changed that needs to be committed. So now we can take a look at the history of what we've done to this Git repository. So we're going to do a git log. And so now we've had multiple commits, and they're showing in reverse chronological order. So this was our initial commit here at the bottom. It has a very long, unique string of characters and numbers. Then we made our small improvement to that description equals line. And that was a different commit with a different unique number. And then we ordered our imports according to PEP8, and that was our most recent commit. So it's important to note that there are these unique identifiers associated with each commit. And that actually makes it possible for us to refer to different previous commits. And that's really the power in Git, is that we can always go back and find what we did before. We don't lose it. So the next thing I'll do is sort of demonstrate how we can keep track of, or sort of access the history of our commits. And so I'm going to make one more small change to our program. So I'm going to open plot precipitation climatology.py again. And I'm going to add a trivial comment here right after the imports. So that's the # or hashtag, and I'm just going to write a random comment. And then I'll save it. And so now we can see what we have. So we'll do a git diff, and this time we're going to give it some information after the git diff. So the most recent commit can be referred to as the head. So let's compare the head with our current version of precipitation, plot precipitation climatology.py. And so it tells us that we have added this random comment. This is exactly the same as if you just do a git diff. So git diff by default compares the most recent commit, which can be referred to as head, with the current version that you have of your file. So that's not particularly exciting, of course, but the real power is to be able to compare with previous commits. So we can refer to previous commits as referenced from the head. ~1 would be the commit before the most recent one. ~2 would be the one to before the most recent one. So as an example, we'll do a git diff, and we'll compare it with the commit prior to the previous one. So that's head ~1. So head is the most recent commit. The ~1 means the one before it. And then plot we'll compare it with our current version of plot precipitation climatology.py. And so now we can see that we added that random comment. And since the commit before the most recent one, we also shifted that import argparse to be the first import statement. So we can see what changes we made in this file over the history of our commits. You can do the same thing. You could say ~2. That would go back to a commit prior to that one. You can even do ~3. But what happens when I do ~3 is it says it doesn't have anything. And that's because I don't have that many commits. I have head ~1 and head ~2. So if I tried to access before that, it's telling me I don't have any commits that are head ~3. So you can also refer to commits not only in reference to head, but in reference to their unique character string. So I can say git diff, and I can use the first 7 characters of any of these commit character strings. I don't have to use the whole thing. If I give it the first 7, Git knows what I'm talking about. So I could say git diff, and I'm going to take this one here, this commit where we did the small improvement where we changed that description line. And I can say EF3C731. So that refers to this commit here. And I compare that with plot precipitation climatology. And it tells me that I added a random comment and moved the argparse. All right, so now we know how to save changes to our files into Git using git add and git commit. We know how to use git status to check that things are going okay. We know how to use git diff to see how things have changed. And we know how to go back in time over the log using git log of all of our commits. So how could we use this to save ourselves from making big mistakes and losing code? So let's suppose we accidentally overwrote our file. I'm sure this is never going to happen to me, but yet it happens many times. So sometimes it just happens and you don't want to lose all of your work. So let's see what happens and how Git can save us from ourselves if we overwrite our file. So I'm going to echo whoops into plot precipitation climatology.py. And then I'm going to cat plot precipitation climatology.py, except I have to spell it properly. I think I messed up this. I think I mistyped here. So we'll echo whoops into plot precipitation climatology.py. And we will cat it again. And we'll see that I overwrote the file. Now the file just contains the word whoops instead of my entire script. So I can type git status and check what's going on. So Git knows I changed the file, but those changes haven't been staged or committed yet. So the good news is I can get it back. So there are 2 ways to do this. If you are on a version of Git that's newer, it's version 2.29 or newer, the command is git restore and the name of the file. I, however, am on an older version of Git. You can see that. And so the command is git checkout head. So it's saying get the version of plot precipitation climatology.py that's in the most recent commit, and I have to tell it which file to take. So we're going to get checkout from head. So from the most recent commit, we're going to get my plot precipitation climatology.py file. And now, if we take a look at this file, I'm saved, I got my scripts back. So even though we overwrote it, we were able to recover it because we had been tracking it in Git. So key points. To initialize your repository, you have to use Git init. To save off your files into Git, you have to add them, and then you have to commit them. You can use Git status to check the status of your repository. You can use Git diff to see what's happened since your last commit. And you can use Git restore or Git checkout to recover old versions of files from previous commits. So that is the summary overview of using version control and using Git. And so now is a good time for questions. I see there's been questions in the chat window, and I think that many of them have been answered. I see a request to cover branches. We won't cover that in this, but Software Carpentry does have a entire lesson on Git that covers those things in more detail. Other questions? I'm not seeing, I see reference to what are Git GUI options. And just so you know, William Gallery, that's going directly to me. It's probably good if you send that to those questions to everyone, so everyone can see your question. I am not, I don't use Git in a GUI context, so I can't answer that question for you. I see a question about, does it work with Python, Shell, Fortran, et cetera? It works with absolutely any file. You can do this with absolutely any file. Git is not unique to Python. So feel free to store anything. So this question says, what are we using? We're doing everything local, not on a remote repository, such as GitHub. Yes, this lesson was about local. We'll talk about GitHub next. I see reference to Git branches, and we're not going to talk about branches in this particular lesson. Ryan, thanks for posting the Git novice software carpentry lesson. We'll go into a lot more detail about different things you can do in Git. And then how do you close out Git once you're done? You don't have to do anything. You just exit your shell or leave the computer. The nice thing is that your code, when you exit, close your computer, close your window, whatever, your code is still nicely stored in that .git. And when you come back, you've got everything safely stored and all the information you need about all the changes you made. Other questions? Oh, good. Thanks, Drew, for posting GUI options. The second restore command. So the command, if you had, so if you have older versions of Git, newer versions use restore, older versions use Git checkout, and then it's head, which is the most recent commit, and then which file to get from that commit. Thanks, Damien. Other questions? If not, then we probably want to go on to talking about GitHub. I will pass it off to, I believe Sarah's next. Let's see, how do I change presenter?
You got it, Kathy?
Yeah, I think so. Hold on. There we go.
Awesome. Thanks, Kathy. Okay, so just gonna get set up here. and I'm going to give you a little intro before I share my screen. So with Kathy, we learned the local side of our version control, but there's another side of things where we can use a remote directory as like our home directory for things. And so Git allows us to do this. Git overall allows us to move work between two repositories or directories pretty easily. So if we're working on another computer or maybe working with other people, it can be helpful to share our code with them and be able to have a master copy that we can both work on. And Git allows us to do this. So I'm going to show you how to upload your code to the internet and allow others to edit it that you give permission to. Okay, so I'm going to share my screen. I want this one. Okay, so you should see this GitHub window that I'm going to make a little bit bigger. Can I have some confirmation that you can see my screen?
Sarah, I just see a white screen right now. I do
Why
see your
does this
mouse,
up?
however.
This, okay.
Now I see your full desktop.
Okay, do you see my full desktop with a like a picture of
Browser?
me?
Yeah,
Yes,
I do.
perfect. This is exactly what we want.
Great.
Okay, so I want you guys to navigate to your GitHub website. I believe Damien sent you an email yesterday or prior to this lesson that said to make a an account on here. So once you've done that, I'll give you a second to do that. And make sure you're signed in. So once you have navigated to GitHub and signed in, we're just going to go to this plus in the upper right hand corner next to your picture. And we're going to click on that. And it will give us this drop down, which I hope you can see. But if you can't, the first option is new repository. And so we're just going to click on that. And it will bring you to this screen. So just to repeat that in case anyone missed it, if you click the plus sign, new repository, will bring you to this screen. Okay, so it will tell you to create a new repository. So first we're going to name our repository, and I'm going to name it Data Carpentry because that's the name of my folder, and that's what you should do as well. It says that this is available, so what this is checking is if I already have a repository on GitHub called Data Carpentry. So I don't have a repository called this on their servers at this point, so it says I can make it. It also gives us some information or some inspiration if we want to use their name for our repository, which is always kind of fun to look at. We can then add a description for our repository. So I'm just going to say Data Carpentry repository. Then next we have this option of public versus private. And so if we choose public, which is what I'm going to recommend we do for this, it means that anybody on the internet can see our repository. They can click through, look at our code. It will render our Jupyter notebooks for them, and they can download and edit it. But they cannot like edit it and push it back to GitHub and change your work basically, unless you've given them permission. So for example, I give my advisor and other collaborators permission to edit my work, but you need to do that manually. And then private hides it so that people can't see it. They can't access your code. It won't even show up if somebody looks up your username in GitHub. And then we have these three options. So you could add a README file, and so what this does is just add some documentation to the homepage of your repository. I'm not going to do that, but when you get more comfortable with Git, this is a nice way to document kind of the project that you have in this repository. You can add a .git ignore, which I'm also not going to go into, but what this does is it allows you to specify different file names that you don't want to be uploaded to Git or to your remote repository. So for example, I use this if I have like very large files that I don't want clogging up the Git process. And then lastly, you can choose a license if you want. I'm also not going to go into this. And then we're just going to hit create repository. And it should bring you to a page that looks like this. So you see that there are some different instruction blocks here. So we're not going to follow those because we've done a lot of that already in the lesson that you just did with Kathy. So we've already initialized and everything. Okay. So at this point, what we've done on GitHub servers is that we've created this new directory called Data Carpentry. We have changed directory to go into that directory here. And then we've done git init essentially, which means we've initialized this directory. So now we want to connect this remote repository to what we have locally. So to do this, we're going to make sure that we have HTTPS here highlighted. So we're not going to do SSH. SSH adds a little extra level of privacy, I guess that's the way you would say it. And I'm not going to go into that because I don't have a whole lot of time to go into that right now, but there are some really great resources about how you can set that up on your own if you're interested in the lesson notes page. So make sure you have the HTTPS selected and then just copy and paste this URL, or just copy it, don't paste it yet. This button also copies it, but I don't trust it for some reason. Okay, so now we're going to go back to the command line that we were just working in with Kathy. You'll probably have commands in here, but I cleared mine just for readability for everyone. And so what we're going to type is git, I hope this is big enough, git remote add origin, and then we're going to paste that URL that we just copied from GitHub, and we're going to hit enter. Oh, I'm on my desktop. That's why this isn't working. I need to CD into my Data Carpentry folder, which you should already be in, but I wasn't. So I'm just going to try this again. Git remote add origin, paste, and then hit enter. So we see that we didn't get any feedback, and so that's a good thing for this command, but we can still check to make sure it worked by saying git remote -v, and then we hit enter, and we see that I have my these paths both fetch and push. So what this means is this is the path we're going to grab from when we grab changes on our remote. This is the path we're going to use when we push our changes or when we upload them. And so we also see that these are both nicknamed origin. And so that is pretty widely used, and that's what we're going to use here. I wouldn't recommend changing that because that's what you'll see throughout the internet if you Google your issues or anything like that. Okay, so now we're ready to upload our changes to GitHub. So we can type git, whoops, I was a little behind, git push origin master, and then hit enter. And you should get a command like this. It might take a little longer than mine did, but this is essentially what your output should be. So now that we've done this, we can go back to our Data Carpentry repository on GitHub and make sure that this has uploaded. So I'm just going to go back to my Chrome window, and I'm just going to refresh this page. And we can see that this should be whatever your last note was that you typed in the -m commit command. Mine was the initial commit because I didn't do all the edits that you did, but yours will say something different. And then you'll be able to see that you have this script and you can click on it, you can read it and all that. You could send it to someone, they could read it. So this is how you would upload it. You've uploaded successfully. But let's say now you want to collaborate with somebody. I want to send somebody this this to download so that they can edit it. So the way that you would do that is that you go to this page and then you click this green button that says code, and then you just copy this URL again. And so I'm going to show you this with a different repository. I don't want to download this one because I already have it. So I've created a like a fake repository for us to do this on. So it's called Shiny Pancake because that is what GitHub suggested I name it, and I said okay. And these are just 2 files that I uploaded. So now I want to, what GitHub calls, clone this repository onto my local so that I can edit it. So what I'm going to do first is I'm going to get out of my Data Carpentry directory, because when I clone a directory, I don't want to clone a different Git directory into a Git directory. That just, it's too confusing and it'll mess things up, at least in my mind. So I'm just going to go back one directory so I'm on my desktop by typing cd ... So now I'm on my desktop and now I'm ready to clone that repository. So I'm going to go back here. I'm going to click on this code button and I'm just going to make sure this is HTTPS again and copy this URL. You could also download the zip if you don't want to clone it and have it connected like this. But I want to be able to push back to this. So I am going to say git clone, and then I'm going to paste that URL in and hit enter. And then that will download everything, and we should have this new repository named Shiny Pancake on our desktop. So let's check this by just saying ls, and here it is. So that's all you need to do to connect your GitHub to, or to connect your local repository to your remote. And so now I will take any questions. Okay, so I see that people were getting lots of errors. And that is not surprising to me because GitHub can have, when you're trying to sync for the first time, there can be a lot of errors. So yeah, now, as Kathy said, there's a break time we'll have, and we can work through those errors now.
Sarah, do you want me to set up a break timer for everyone now?
What do the other instructors think about that? Do we want to try and set up a break timer to work through these questions, or should I try and work through these?
Yeah, I mean, I think during the break we can work on any specific questions people have if they've had errors when they were pushing and things like that. Maybe we'll just ask if there's any more general questions about Git and GitHub before we start the 15-minute break. And then obviously if you've successfully pushed and stuff and you don't have any questions, you can go and have a coffee or whatever for 15 and come back. But is there any other general questions about Git and GitHub?
Yeah, a lot of the issues that people seem to be having, I think, are configuration on your machine. So we'll just need to work through that a little bit. And so the people who missed the commands, also all of these commands are on that lesson too. So if you were a little behind, you can follow through that, and it has all the commands. Okay, so we had a question: when you do git push origin master, should you see all the files? That's a good question. So in the lesson prior to this, we had we'd staged our files and then we committed them, but the only file that we were really working with was our the one file that I ended up with staged, the .py file, I believe it was. So if you follow it along exactly with Kathy's, I think you should only have that .py in your remote repository. And I'm just gonna pull mine back up. So yeah, this plot precipitation.climatology script is the only one that you staged and committed, so that's the only one that will be pushed to here. Somebody says git config username and username at GitHub the same one. Yes, oh no, is that username space is your actual name, the name of the user? Is that correct? Yes, that. So that would be, for me, it says Sarah Murphy, so that when I push to GitHub, it says Sarah Murphy made these changes. Okay, so I guess we can probably start the break timer now, and we can start to troubleshoot people's things.
If you need me to give any audience member screen sharing privileges, I can help with that.
Okay, thank you. Thank you, Ryan. So for your Conda environment with the Jupyter Notebook, if you have a separate environment that you are working in, that's when you need to do your Conda activate command. So for people who didn't set up a separate environment and just installed in there, like without creating an environment, essentially, you'll be able to type Jupyter Notebook and it will just open and you won't need to activate anything. So I think that there is essentially one activated, I guess, and to answer your question in the chat. Okay, so does anybody want to share their screen or anything with their GitHub so that we can troubleshoot?
I see Elliot's hand up. I don't know if he wants to.
Okay, yeah.
Oh, he just wants the mic. He said, Elliot, you should be able to use the mic.
Hi, I just have a quick question. Can you hear me?
Yes.
Yes.
I just have a quick question that has to do with if you go ahead and you push, let's say you push a couple of files up to GitHub, and then you decide to add more things on your local repository. Do you then go ahead, can you clone back upwards so that everything stays in sync, or do you have to add things sort of file by file?
No, you can, if you go through, and the way that I usually use GitHub is that I add my entire directory to the staging area. And I don't know if that is typical, but what I usually do is when I'm done coding for the day, I will type git add and then the asterisk and then git commit everything up to it. And so I just do that at the end of the day. And so you can just keep pushing to it and it will just keep updating it. So all you have to do is that same git push origin master, and that will update it on the remote side.
Thank you. That helps.
One thing I wanted to add there is the best way to think of this is in terms of commits. Don't think about it as pushing specific files, because Git works at the commit level. So what you do when you're doing a push isn't pushing a particular file so much as it is pushing the commits you've made over time, which could be at the end of the day one big commit of everything, or for some of us it's more incremental throughout the day. But it's very much you're pushing the commits, and those may or may not be new files. They could just be modifications to files or whatnot.
Yeah, thank you. That's a good way to describe it.
If someone wants to, oh, sorry. If someone wants to use the mic, I saw that in the chat. Can you just raise your hand so I can easily find you in the attendee list?
Real quick, somebody DM'd me and said that the username and password was prompted. And yeah, the first time it may prompt you for your username and password. So that's not unusual, and that doesn't surprise me.
Shimao, you should be good to go. Okay, I'll go to Thomas Adams. Thomas, you should be able to unmute yourself.
Okay, what I'm showing in the GitHub is just a README file. I don't have my Python file, and I did the git push origin master, and I tried it a second time. It says everything's up to date. So what can I try now?
Git status.
Git status.
Thomas, do you want to share your screen, or do you want to just do the?
I'm on two different computers, so.
Well,
I can't.
Okay, gotcha.
I'm connecting through GoToTraining through my Mac, and I'm doing the work on a Linux box. Okay.
Gotcha. Never mind then.
Yep. What do you want to know from using Git status?
What is like the last thing it says?
Nothing added to commit, but untracked files present.
Okay. So it seems that you have nothing in your commit space to push to your remote repository. So you might have staged files that have not been committed. Does it say that? I wish I could see your screen.
Yeah, sorry.
Oh no, it's okay.
I mean, Git log is showing, a number of things, changes that we've made through the tutorial. So.
Did you try refreshing the remote again? It might have just taken a minute to update.
Okay, I'll try it. Nope.
Okay. Can you try, hang on one sec.
So Thomas, in your local repository, you just have the plot precipitation climatology script, and then on your remote repository on GitHub, you just have a README file because you clicked the box to create a README when you created the repository. Is that right?
Actually, I don't seem to have my plot precipitation climatology.py file. I don't know where that happened. What happened to that?
Can you see it in your history, your Git history?
Is it with a ==?
I don't remember the exact. Might be git log is the command.
Yeah, I did log.
Okay.
And I mean, I see the comments like, see, are they in order? Like initial commit of precip climatology.
So what happens if you type git pull origin master?
Script, and then small improvement to help information, then ordered imports according to the echoing the whoops into the file, and then I thought I used the correct command to check, had to use the git checkout head command, and I thought that worked, but maybe it didn't. Let me try again. I mean, the file does show up if I just do, you know, an ls command.
Okay, great.
So
So yeah, like Damien suggested, can you try git pull origin master from your just to, what that's doing is grabbing your remote and bringing it local.
git pull.
Yes. And then origin master.
Right.
I'll put the command in the chat too.
No, I got it. And
Okay. Whoops. I sent it to
and it
organizers
says
anyway.
what I get back is star branch master and then an arrow fetch head already up to date. Okay, let me try. Hold on, let me try.
So you could try. Sorry, go ahead, Damien.
I was going to say you could put the URL to your GitHub page in the chat, and then we could view that.
Okay.
And so I was just gonna suggest you could try git adding the file again and then git committing and then
Right.
pushing, starting from the add step.
Okay, I've sent it. I've left out the https://github.com.
Okay, that is fine. Okay.
Yeah, just in answer to Cecile's question, I think everyone who's got a GitHub account's been getting those emails lately about GitHub saying that it's their password. I think soon they're gonna be changing things to make things more secure. And so instead of passwords, I don't know, there might be two-factor authentication, or you might have to use the SSH instead of HTTPS. I've actually just been ignoring it until it makes me do the more secure thing. But I think eventually you'll have to do some kind of two-factor authentication, or you'll have to use the SSH instead of HTTPS method or something. So yeah, there's some links in the notes about SSH and everything, but I don't know if others have read the GitHub security changes in detail, but so far I've been ignoring them.
I have also been ignoring them, so on the
I
same
have
page
also
as
been
you.
ignoring them.
Yeah, so you're gonna have to create a separate key. You can no longer do git command line stuff with the same password you used to log into your GitHub account, is the upshot of it, for various security reasons. So that's what I think all the emails are about. I haven't seen them because I haven't been using authenticating that way.
So I'm sorry, I may have missed what you were saying. Is there anything I can try to get this up there that hasn't worked?
Yeah. So I would try, did you try starting from git add and doing git add and then the file name, then committing and then pushing? Just starting from the first step.
Actually, before you go there real quick, can you do one thing and type git remote space -v?
Yeah, I just want to let you know that we have another person who's also got a question and wants to share their screen.
And it looks like it's pointing to the correct URL.
To the,
Does it have both fetch and pull?
Yes.
and it's
Okay,
pointing to TEAII/Data Carpentry.
Pardon?
It's pointing to your TEAII/Data-Carpentry.
Yes.
Okay.
Yeah, I might have to go with Sarah's suggestion of kind of starting all over, following the notes.
Right. Go ahead to somebody else. Thanks. I appreciate it.
Actually, yeah, I can see right. If you go to the main page, it's going to the main branch. If you go to the other one, it's master, because recently GitHub has changed the default branch name. When GitHub creates a new repository, the default branch name is now main instead of master. But when you ran Git locally, it created master as your default branch. So you have two branches on this. So we weren't trying to talk about branches today, but there's the answer to the question of why it looks so weird. Anyone want to try and give a brief explanation of that? Because I don't know, I can do it briefly.
Well, it's sort of like having, oh God, I don't know if I can. All I know is with GitHub websites, there's like one copy that is the one that the website is, I don't know.
So the upshot, if you want to see the changes you made, if you click this box that says main in the upper left portion of your the screen on GitHub, you can get a drop down that says branches, and if you click master, then you'll see your plot precipitation climatology.
So is that because of the initialization with the README that the main happened? I see.
Yeah.
Okay.
Yeah. So if you create just a local repo using Git and Init and everything that we just did, you'll have master branch. And then if you push that to an empty repository on GitHub, then you'll just have a master branch. But if you initialize a repository on GitHub, and then you say you clicked yes, have a README file, then it'll create a repository with a branch called main, and then that's where the problem comes. Yeah, so you can avoid it by creating a completely empty repository on GitHub, and then when you push to it, you get master like on your local one. But if you start the process the other way around and create the repository first on GitHub, and then say pull it down to your local computer or clone it or whatever, you have main instead of master, which is a bit annoying.
I did not realize that. Thank you for catching that. Oh, sorry, go on.
Oh, I was going to say, do we want to share the screen of the other person that had a question?
That was what I was going to say too.
Yeah, we'll field one more and then we might move on.
So, Shimao, you should be the presenter now.
Right now, can you see my screen?
Not yet.
How can I do it?
There is a button you can click in the sidebar that looks like a computer screen. And there is also a screen sharing section in the control panel that you can click the play button for to show your screen. Does that make sense?
I don't know. Right now, you cannot see my screen. Can you?
Not yet.
I have two laptops, so I'm trying to close one.
So the key is you need to look for the go-to training control panel, because that is how you can activate your screen sharing. It does not do it by default when you become the presenter.
It takes time. I see. Let's see. Let me close one. I close the one, on my Mac. I'm trying to use my PC
Okay.
right now.
So I'll make the one that's still open the presenter.
Right now
if
it
you
should
can
be
share.
fine. You should be okay. You can see my screen, Sarah?
Now
I
we
can,
can.
yeah.
Here is my problem. Right now I'm right here. You see here, Xiaomao,
Yes.
and then this one. I stopped here. I cannot do anything else. And then I tried to copy this one into the, and then I couldn't move to the next step.
Okay, so once you copy that, you need
Yes,
to
I
go
did.
into a terminal window.
Yes, Control C. And
Oh, I can't see a
yeah,
terminal window if you've opened one.
this screen is so tiny, sorry. And let me
Okay.
find the, where's my terminal window? Let's see. It's right here, right?
Oh, yes, I see it now. Okay, so what you
And
want to
then-
do is you're in your Data Carpentry directory. Okay, so what you want to do is type git remote add origin. So you did.
I think the issue, the issue is that you're not at the bash shell, so you need to use the git bash program. You're in a PowerShell. The Windows PowerShell doesn't accept like bash shell commands.
Oh, makes sense. So how can I do that, Tim?
So in the software installation instructions, it asks people to install who are on Windows to install git bash. So if you,
I did. I think I did.
Yeah, so if you open that, then you'll be able to use bash commands and do all these things. But at the moment, you're in a PowerShell, which is a whole different set of commands. So maybe between now and the next break, if you have a go at getting git bash running on your machine, and then if you have any issues, we can help you out during the next break.
Okay, thank you. Yeah.
No problem.
Thanks, Damien.
Thanks.
Yeah, sorry about all the issues with that, everyone. GitHub can be a little tricky with everyone's different machines, but I'm glad that we got there for most of you, and we'll keep working with it.
Who would we like to be presenter now?
Me.
Sorry, that was Damien that said that?
Yep.
You're up. And we're still recording.
Cool. So hopefully you can see my screen now.
I see a Jupyter notebook.
Cool. Yeah, so basically now that we've obviously developed our plot precipitation script, we've got it, we're tracking the changes using Git, we've pushed those changes to GitHub so we've got a backup, we can share it with people and things like that. So now we're kind of going to settle back into the rhythm of making further edits and improvements to the script, and we'll settle back into that rhythm of basically you just watching while we do some live coding, and then you guys having a go at some challenges in a breakout room after that. So no need to copy down everything I'm typing here, just watch and kind of take it in, and then during the challenges you'll get an opportunity to try these things out. And so here, basically the next improvement that we're going to make to this plot precipitation script is to have the script apply like a land mask or an ocean mask to the data. And that's a common thing. Obviously, sometimes when you're plotting precipitation, you only care about precipitation over land or over the ocean. You don't care about both. And to do that, we need a way of basically determining whether each grid point on our map is a land point or an ocean point. And so you can see here that I've set up a new notebook that I'm using. I've imported NumPy and Xarray, and I've defined this sftlf file, which is another CMIP6 data file. It's the land area fraction file, and it tells you what percentage of each grid cell is land. And so I'm using the open dataset command again to open this dataset, and I'm extracting the sftlf variable. And so if I run this cell and print that, you can see that our X-array data array here is a whole bunch of basically zeros and 100s. So most of the grid cells are either 0% land or they're 100% land. And so, yeah, the variable is the land area fraction. The units is the percent. And so it ranges from 0% to 100%. And so if we were going to now go ahead and do this task of making a decision on each grid point about whether it's land or ocean, our first instinct might be to first obviously create a data set for our precipitation again. So I'm in a brand new notebook. So open data set, and then in my data directory, I want the precipitation data file for access CM2. So run that one first. And then like we did a couple of days ago, we create our climatology again by taking the precipitation variable from that X-array data set, and then calculating the mean over the time axis. And we want to keep the attributes like that. And so our first instinct might be to, we'll write a loop, right? We'll loop over every grid cell and we'll make a decision as to whether that grid cell is land or ocean. So our first instinct might be to be like, so we'll get the number of latitudes and the number of longitudes out of this, out of our array by asking for the shape of our data array. And then we could go, okay, well, for Y in range and lats, so loop over each of the latitudes. For X in range and lons, loop over all the longitudes. And then at each grid point, ask the question if the SFTLF, is that what we called it? Yep, if SFTLF dot data at the Y X point is greater than 50%, then that's obviously a land point, and so we want to mask that. So we could go clim.data Y, X equals numpy.nan. So that might be our first kind of impulse, is to write this loop over each point in the array, ask whether the array is a land point, and if it is, set the value to it and not a number value. And the problem with that, and this would probably, I won't execute, or maybe I will execute it. No, I won't execute it, but basically this would probably work okay in this particular example, because I don't think this array is that big. Oh, yeah, it's like what did we see yesterday? It was 100 and something latitudes by 100 and something longitudes. That loop might not take too long, but often the data arrays that we're using are much larger than that. If we've got like a 1 degree global grid, it'll be like 180 by 360 points. If we've got a super high resolution model, it could be thousands by thousands. And looping in languages like Python and R and MATLAB is quite slow. They're high level languages that are written to be very readable to the human eye. And so it's very easy to kind of edit and develop your code. But the downside of that is it's kind of slower for the machine to run that code. Whereas if you've come from a background where you've done some Fortran coding or some C coding or something like that, low level languages, which are less readable to the human eye, but are faster for the machine to run, you'll probably be quite familiar with, and you might be quite comfortable with writing loops like over large arrays because it happens quite quickly. But the problem with high level languages like Python and R and MATLAB and things is that looping can be quite slow. And so if you find yourself wanting to do something to each value in a large array of numbers, and you find yourself writing a loop in a high level language like Python, you kind of need to stop yourself and go, there's probably a function out there to do this more efficiently. And so basically a lot of the NumPy routines are what they're called vectorized operations. They have a whole bunch of functions that will apply kind of like the same operation to all the points in an array at one time. And they're usually written in a fast, low-level language like C under the hood, but you don't need to know that or see that. You're just typing Python NumPy commands, and then under the hood, it's using some C to do some loops really, really fast. And so this kind of, they're called vectorized operations, where you can act on all the points in your array at once. And so we've caught ourselves in this example writing a loop, and we should think to ourselves, oh, we're writing in Python. That's potentially a slow thing to do. We should see if there's like a NumPy command that does this over the whole array at once. And fortunately, in this case, there is. And so what we can do is, if we get rid of our loop that we don't want to use, execute that one there. So if we wanted to define a variable, let's say clim ocean, which is our data set with just the ocean points with the land points masked, what we could do is we can basically, there's a function called numpy where, which basically makes a true or false decision at each point. And so the nice thing, as we were talking about in the first day's lesson about how the developers of Xarray have built a lot of NumPy in, they've actually built in the where command into the NumPy data arrays, and so we can access that. So we can literally just type climatology where, and we want where sftlf.data is greater than, sorry, is less than 50%. And so that's literally one line to do what we were going to do with that whole loop before. And we basically just say, we only want to keep the values in our climatology array where the land surface area fraction is less than 50%, so the ocean points. And so if I run that, and if we look at clim ocean, you can see basically the array now has, it's 144 by 192. It has a whole bunch of NANs wherever there's land, and it has actual values wherever there's ocean. And so in one line, we've done what that loop would do. And so, yeah, this is a very short lesson, basically just to get you to start thinking about using these vectorized operations that the NumPy library offers, rather than writing loops. And so the challenge for all of you at the bottom of the lesson notes of the vectorization lesson is to basically implement this masking functionality in the plot precipitation climatology script. So take the version of the plot precipitation script you were using during the Git lesson, and follow the challenge here to basically add a mask option where the user at the command line can say whether they want the ocean masked or the land masked. So if there's no kind of burning questions, I might get Rex to create the breakout rooms, and then you can all have a go at implementing this mask option on the script.
Sure. I'm going to stop recording if that's okay, Damien.
Let me just change presenter here if I can.
Sure. I'm just recording in the background now.
Cool. There we go.
Sharanjit, we can try to give you a longer warning. Sorry about that.
All right, hopefully everyone can see me and see my screen okay, just to confirm. I get a confirmation from somebody that the screen is visible.
Yeah, Kathy, I see your whole desktop.
Okay, great, thank you. So the next section here, the next lesson we're going to talk about is defensive programming. And kind of to motivate this, I don't know about you, but one of the last things I want to happen is to find out after I've submitted and published a paper that there was an error in my code and that my results are not what I thought they were. That's certainly not something that none of us want to have happen. And so I do a lot of testing, a lot of looking at my data from a physical perspective, making lots of plots, trying to understand for sure that that my code is working properly before I get to the stage that I'm submitting a paper. And so we all want to make sure our codes are producing reliable results. And we have to assume we're going to make mistakes. And so we need to guard against these mistakes. And besides making lots of plots and looking at our data and trying to take a physical understanding perspective, we can also take advantage of the programming language to help us to do defensive programming by adding in assertions in our code. And assertions are simply a check to make sure that certain things are true for our code to let us know if something that should be true isn't true, and to stop and say, hey, there's a problem here. So that's what we're going to learn about in this lesson. So I'm going to give a quick example, and I'm going to show it in a Jupyter notebook. And it's the example that's in the materials, which I'll repost to the chat window, that one to the organizers. I'll repost it to everybody in case you want to follow along in the lesson materials. And so suppose that we had rainfall observations, and we had, I don't know, value of 1.5, 0.3, 0.7, minus 0.2, and 4.4. And so one thing we could do is we could kind of check our total rainfall and see if total rainfall makes sense for the area that we're looking at. So I'll write a loop here where I start my total at 0.0, and then I go through all of my rainfall observations. And as I total up, one of the things you'll notice in my rainfall obs, if I'm looking at total rainfall, I've got a negative value here, and total rainfall should be should always be positive. So that's something I would want to catch if I had some bad data in there. So I can actually write an assertion statement that will allow the program to check that for me. And that's done with this assert, and you can see it changes to green because that's a special word in Python. And it checks to see, I'm going to check to see if something is true. So I'm going to check to see that my rainfall is greater than or equal to 0.0, which is what it should be. And if it's not, I can print a statement to notify me that I have this error in my data. So I'll say rainfall observations should only contain positive values. I'll try to make this a little bigger so it doesn't. There we go. So now I have a check. It's checking if this is true, and if it's not true, it's going to print this statement and stop the program. So I will keep totaling up my rainfall. And then after I go through this loop, I'm checking if the rainfall observations are positive. If I can keep going, I'll be totaling them up. So I'll have the total rainfall for all of my rainfall observations. And then I can print total rainfall is total. And so when I run this, I get an assertion error. And so it's identified as it's running that something in here is not, that this statement here is not true. And so it's printing this statement here that says rainfall observations should only contain positive values. And so if I had only positive values, it would of course run to completion and give me my total rainfall. But since I had this erroneous data, it actually catches that for me and lets me know. So it's pretty valuable to be able to have the program check for you what's happening and tell us that there's an error. So I'm going to now move over to a terminal window. And just to be clear, I'm in my Data Carpentry directory, and I have activated my environment. So I have access to all of my standard import packages. So we're going to go back to our plot precipitation climatology program. And so that's why I've moved over to the terminal window. And so let's think about how assertions might be useful in the context of that window. And I'm going to close my notebook so I won't get those messages. There we go. So let's look at an example of how being able to do this type of assertion would be helpful in our program. So I'm going to cut and paste an attempt to run this program from the lesson materials. Try that again. Okay. So I cut and pasted this line where I'm saying Python, I'm calling plot precipitation climatology.py. I'm giving it the input file. I'm telling it which season I want. I'm telling it the name of my output file, and I'm giving it this -mask option that you all used in the last practice in the last breakout session. And I'm giving it the mask file, and I'm saying I want to mask out. I'm saying I want to mask out land. I'm going to run that. It'll take a minute. I'm running on my local laptop, so it takes a second here, but it seems to run. And I'm going to open in the file browser, desktop, Data Carpentry. And here's this one this file that just ran or just created. So I'm going to click on it. So the way the masking worked is it was supposed to mask out land and plot ocean. Well, what actually happened is that it masked out ocean and plotted land. So let's see if we can kind of understand why that happened. We'll understand that using the Python debugger, and then we'll take advantage of our knowledge now of how to use assertions in order to sort of keep that from happening in the future. So I'm going to open now our plot precipitation climatology.py file. And I'm going to use the Python debugger. So I'm going to add it an import statement. The Python debugger is called PDB. And then I'm going to go into my apply mask function, which is here near the top. And since the masking is what didn't work properly, it picked the wrong thing. It masked out the ocean instead of the land. Right before the part where it does that, right here, this if statement, I'm going to put a trace. So I do that with pdb.setTrace. And what that does is it will actually stop the program here where I said set trace, and it will allow me to interrogate my code by, say, finding out what the values of certain variables are, and then stepping through line by line. So I'm going to save this, and I'm going to rerun here the same command I ran before to try to run where I'm doing JJA and trying to mask out land. And so now the program has stopped. And I can see what's going on. So I've stopped here, and I know that the problem with my program had to do with masking of land, and that's based on the value of the variable realm. So I'm going to print realm and see why this if statement didn't work as it should. So what you can see is the value of realm is land with a capital L. And my if statement was checking for land with a lowercase l. So that sort of gives me an idea that the reason my if statement for picking the land, masking out of land versus ocean didn't work properly because I didn't take into account accidentally capitalizing land versus all lowercase. So in the Python debugger, I can say, well, I think this is my problem. I'm going to check and see if I can solve it. So if I say realm equals lowercase land, I'm going to change it. And then I can use the in character to step forward, step by step, one line of code at a time to see if this fixed my problem. So now it's gone through this loop, and I can see that it makes sense. It's now going through the loop where I expect it to. And then once I'm satisfied that works, I can press C for continue. and that'll allow it to continue and complete the program. So now I've completed the whole program and I'm outside of this debugger and I've got my command line prompt back. So now I can go back to my file browser and I can see if my landmass worked properly. So now, since I fixed it by hand in the debugger, I'm now getting the right plot. I'm now getting the land masked out instead of the ocean. So now we know what the problem is. We can go back to our program and see if we can see how we might be able to fix it using assertions. So I'm going to open up plot climatology, plot precipitation climatology.py, and I'm going to go to my apply mask program. So now what we can do is replace where we have this set trace. We can replace it with an assertion that checks that the land is spelled with all lowercase or ocean is spelled with all lowercase, so that we have things correct. So I'm going to delete this line here. I'm not going to need the debugger anymore for this particular problem. There we go. And I can put in this assertion statement where I'm going to assert that realm is in land or ocean. So I'm checking to see if this is true. If the realm variable is in this list, land or ocean, then I can have it say, if it's not, I can say valid realms are land or ocean. And you see I had to do some extra quoting here to handle the fact that land and ocean also need quotes around them. So now I can check. If the realm is in land or ocean, then the program will continue properly. And if it's not, it's going to stop and give me this error message. So I'll save that and I'll run this again. Again, I still have my capital land here, so we should get an assertion. And it does catch that I have realm set to something that's not lowercase land or lowercase ocean. So that's really sort of a basic idea of how we can use the programming language and the assertions to do defensive programming and allow us to check our programs for us so we don't make mistakes. I would also suggest that you, I did not set up the GitHub repository for this particular lesson, but you could, now that you've added this, you could do a git add and a git commit, and then push that to your GitHub repository with git push origin master in order to save off this new working version of your program. So to summarize, you want to program defensively to help find and avoid mistakes. Assume the errors are going to arise and write code to detect them when they do. You use the assertions to do that. And you can also use the PDB, the Python debugger library, to help you step through your Python script and identify sources of errors. And there are places through Software Carpentry where you can get more advanced lessons on code testing if you'd like to be able to do fancier things than what we've shown here. So I'll stop there and take questions.
Hey, I'm going to unmute Mike, who has his hand raised.
Okay.
Mike, you're on air.
I didn't have my hand raised. I'm sorry.
Oh, I'm sorry. It looks like it's up. I'll put it down.
Are there other questions about defensive programming and using assertions?
Scott, do you have a question? I'll unmute you. If you have a question, you're on air.
Yes, I'm curious. I like this, but wouldn't you normally want to, I don't know, set, if it's a case, wouldn't you want to set the value maybe to run a lower function against that incoming option? That way you don't care what case they put in. I know this is a limited example, and I'm really grateful because I needed this yesterday. So thank you. But I am curious about, wouldn't that also be defensive programming, or is that different?
Yeah, I think it's the same idea. Is anything you can do to check and confirm that your program is doing what it's supposed to, and there's not unexpected errors. But yeah, actually, my personal solution to this particular problem would just be to lowercase whatever comes in, but also to check. I could put in junk there, right? If I put in right, I would want it to catch that. But I could have it lowercase, whatever I put in, to guarantee that maybe if I had land or ocean and I included an uppercase in there, that at least maybe I'm fixing that and letting it continue. Other questions? All right, I'm not seeing questions.
Yeah, I don't see any.
I think we could go to breakouts if other instructors are okay with that.
Okay, so this section we're going to talk about data provenance. And so this is essentially the history of what you're working with. So we have history in our the files that we've been using, and now what we're going to do is work to create history within the figure that we've created. So there are some command line tools which insert a record from the command line, and those were used when these files that we've been working with were
Hey, I'm not sure if it's just me, but I can't hear you anymore, Sarah.
Yeah, she also cut out on me as well. I can't hear her.
Oh no, there's no sound?
Now it looks like it's just a
Now
little
you're
bit
back.
intermittent or laggy for you. Your screen
Oh,
share seemed to be pretty good, but we'll let you know if we can't hear you again.
okay, interesting. Does that have to do with my microphone? Does it seem?
It seems like as far as muting settings go, you were fine. I'm not sure. I think it's an internet connectivity speed issue, most likely.
Oh, okay. Sorry about that. Yeah, I live in an apartment and sometimes my internet speed gets a little not great. So I apologize for that. But right now, I don't know how much of that you caught, but right now we're just looking at the history of one of our netcdf files that we've been working with. And then after, we are going to put our own history into the figures that we've created. So I've just imported Xarray because I just want to open a data set with Xarray to look at the history so we can get a feel of what we're working with. So I'm going to define a variable and I'm going to call it XS ESM 15 PR file. And then I'm just going to put the string here for my file. So I had that on copy. You can put whatever your path is there. So now I'm going to set that data set to a variable. And now I'm going to print out that data set's attribute that is history. I spelled attribute wrong, but now we get that history. So when we look at this, we can see here we have a date and a command that was issued at the command line. and so on. So this is everything that was done to this file. Now to save this, we can't just write a string and hope that it saves there. We need to import a library, and then that will help us do this. So I am going to go back to our script that we've been working with, which is our plot precipitation.climatology script. And I'm just going to open it here to work with it. So I am using the command line prov package. So I'm going to write import cmd line underscore provenance as cmd prov. And I always spell provenance wrong. Always forget some extra letters there, but make sure you spell it right, and then that is how we'll import it here. So now I want to go into the script and add into the save file, telling it that we want some metadata. So I'm going to scroll down to our main part of the program where we were making our plot. So I am going to put this just below the create plot, but above the saving plot, I'm going to say new underscore log. So I'm setting a variable that is going to be the information that we are putting in our log. And then I'm going to use this package that I just imported, .new log, which is one of their commands that creates a record for you. And then I'm going to say in file history equals inargs.pr file. So we're saying that the history is going in our file that we put in there. And then dset.attrs history. Whoops. And I need to make sure I have the right number of parentheses there. And so then I am just going to set a tracer like Kathy did in the last lesson, because I want to be able to look at new log. And I see that I've actually wrote netlog both times, and this should be new. I apologize for that typo. Ooh, I typed in file. Typed everything wrong here. Okay, so now I'm just going to add the tracer. Set trace. And then I'm going to specify the metadata in here. So I'm going to say metadata equals history, capital H, and then new log. So what this is saying is that when we create this figure in the metadata in the history field, we're putting the information in new log, but I spelled it netlog again. And then that should be all we need. So let's save this. And now I'm going to try and run this from the command line. So I'm going to go back to the command line. And so I'm in my Data Carpentry script. I'll make my font a little bit bigger and make sure that I'm in the right directory. And so now I'm just going to use one of these same commands that we used before, just using Python and then the plot precipitation climatology. I've copied and pasted it because these are long names for the files, but I have Python, our script, the data file, and our input, and then the PNG file name. So now I hit enter, and it'll take a second, but now we see that we have PDB. So now let's look at what our new log variable has in it. So we can see that our new log variable now has this history in it, just like what we saw in Python. So now we can get out of this by just hitting C. Okay, so now that we have written our metadata like this, how can we view it? So we know that we've created this file. We know that we've put metadata in it, but that's not super helpful if we don't know how we can actually look at the metadata. So I am going to use a new package called exif tool. And so to install this, you would type conda install exif tool and then hit enter. And I've already installed this, so it's just going to go through this and then tell me that I already have it installed. So it's already installed on my machine. But if you don't have it and you wanted to follow along and look at this metadata, you would need to install it this way. So now that that is installed, I'm just going to use it by typing exif tool. And then I am going to put in the name of the PNG file. And so that is this. So I just did some tab completion there. And if we hit enter, we see all the metadata associated with this file. And so we can see some stuff that was automatically generated, but then this history section, this is the part where we where what we did is contained. And so we can see here that this is the command that I executed. So we have Python, our .py script, and then the NC file, and then our PNG. So it worked, and we recorded it, and that's great. But this is a little hard to read. So before, you might have noticed that when it would have been like a new line, if you were formatting it to be like super visually appealing, there was a /n, but now we don't even have that. So there's really nothing to tell us that this is a new entry from the previous one other than the fact that it has a date. So let's edit our script just a little bit more to make that a little more clear. Another issue that we're going to need to deal with is that this history key that we're using here within this metadata is not the same for every file type. So history is specific to .png, and there are different specific words that are that go with different file types. And so you will explore that a little bit in the activity after this. But for now, we want to make sure that the user isn't inputting something other than PNG so that we don't run into an error. So now let's go back to our plot precipitation climatology script that I have here, and let's edit it a little bit. So let's go to the main section here that we were just in before. And I'm just going to go down to where I had that tracer, and I'm going to get rid of that because we don't need that anymore. But now I am going to edit my new log a little bit. So I'm going to say new log equals new log dot replace /n. And then I am going to replace that with 2 spaces and then end in caps lock, and then 2 spaces again. So here we are going through our new log, and every time we have a /n, we're just replacing it with this end because that's going to be easier for us to pick out when we are printing out our metadata. So we'll know when a new entry starts. So secondly, I'm going to add the assertion just like we did previously, but now I'm going to do it for image format. So to do this, first I'm going to add it up here because I want to add this before we're creating this log. And I'm going to say first image format equals in args dot output file dot split. And I'll explain what this means after I'm done typing it. And then in hard brackets -1. So what this is doing is setting a new variable, and it's taking our output file that we put into this, and it's splitting that string up by the period character. So if in our case, or in my case, I have that period only at the end of the file name before the .png. So that's going to split our string into 2 strings. So we have one that's pretty much our path and then one that's PNG. This denotes to take the last one, and so our last one is going to be the .png. So now image format is a string that is ideally .png, but if it's something else, we're now going to check for that. So we'll write assert like we did before. So we're going to assert that the image format is equal to .png, or just PNG because we split on the dot, so there's no more dot. And then I'm just going to put the error to be only valid image format is .png. And so now we can save this and try this again. So now I'm just going to run this same exact script. I'm going to bring this up just a little bit because it's by the bottom of my screen. I'm going to run the same script I did before, Python, our script, the input data, son, and then our same output file. Just going to run that again. And now we can look at the metadata again. So I'm going to do again exif tool and then the name of our image. And so we can see that what we just did was saved because we have the 2 spaces and end between each of these entries. So let's say we wanted to check and make sure our assertion is working. So let's say that I wanted to try and make a JPEG. And we'll run this and it will say that our only format is PNG. So we see that what we've done is working and it's making sure that it's a PNG and we have our history saved. So that's just a brief overview of how we can save some metadata. And now there are 2, I believe, exercises that I will pull up and show you briefly. And then we'll break out and work on those. So this is defensive programming. We are on this one. So now down at the bottom, first off, we're going to look at the savefig documentation. And so that link is in this, but we can also put that in the chat. And so that will have information about the keys that you need for these other types of image formats. So that will be what replaces history, depending on the image format. And so use that to create a new function that deals with that so that we make sure that we are checking what type of image we're generating and then making sure we're using the correct key for that type of image. And then we just have a second one that is about the netcdf files that I don't know if we'll have time to get to, but if you do have time, you can try and work through that. So I am ready for the breakout rooms now. All right, well, I hope the activity went well, and thanks everyone. I'm going to hand it off to Damien now for the last section.
Cool. So, lucky last lesson, we're going to start talking about dealing with big data, or we called the lesson large data because people have different ideas of what big data is. But basically, at the moment, we've obviously been playing with very small data files that fit comfortably on our laptop, and the data processing's all happened very quickly. But what if, for instance, we had a high resolution model? This is a French CMIP6 model, and the HR means it's their high resolution version. And we're looking at daily timescale data this time for precipitation instead of monthly. And so we've got this high resolution, high spatial resolution, high temporal resolution data. And let's say I want to calculate the daily maximum rainfall across this 160 odd years of data. And so if I do LSLH here and look at the size, each of these data files is 6.7 gigs in size. So I've got 40 something gigabytes of data here, which is more than the available RAM on my laptop. So we're going to need some solutions here to be able to process this data. I'm not going to be able to just read in 45 gigabytes and process it all at once. And so for this lesson, I've downloaded the 45 gig of data onto my laptop. You won't be downloading 45 gigabytes onto yours, and the exercises that we do at the end of this will talk about some of the issues and approaches to dealing with big data, but we won't actually get everyone to download 45 gig. That would be a little impractical. But I'll start a new Jupyter notebook in this directory here, where I've got this bigger high resolution data set. And let's get this out of the way. Oops. Oh, my mouse is acting up, sorry. So if we start a Python 3 notebook here, and so the first thing I want to do is I need a list of those files so I can work on them in the notebook here. And so I'm going to use a rather unfortunately named library called glob to get a list of files. And it kind of acts like, you know, if you do ls at the command line and you do a star as a wildcard, and it'll list all the things, you know, if you do star.nc, it'll list all the files that end in nc. You can do those kind of wildcards in Python using glob. So my list of precipitation files in this case, which I'll call PR files, I'll zoom in a little more. I'll use glob, and then it has a function in it called glob. So I need glob.glob, and then I want all the PR star.nc files, all the files in this directory that start in PR and end in .nc. And then I want to sort that so they're in order, chronological order, because the dates are in the file names. So I can do PR files dot sort. They will sort them. And then if I print them, hopefully we'll get a list of files. Huh. What happened there? I shouldn't do equals. There we go. There we go. There's our list of files in order. I'll get rid of this one. Cool. So we've used glob, and now we've got the names of the files in the list. And what we can do is Xarray will let you read in multiple files and act as if it's just one data set and not a whole bunch of separate data sets, which would be very convenient. So I'll import Xarray again, because this is a new notebook, Xarray. And then I want to define my dset variable again, but this time I'm using the xr.open_mf dataset. So I want to open a multi-file dataset with Xarray this time. And then I need to pass it the list of files that I'd like to read. So that's my PR files variable. And I'll get back to why I'm doing this in a minute, but I need to define this. I want to define the size of the chunks that are read in when it reads in the data. So I'd like it to read it in chunks, and I want those chunks to be along the time axis, and I want them to be 500 megabytes in size each. And so I'll come back and talk a little bit about why I've made that decision in a minute. So there we go. I'll read that in. And then if we have a look at this data set, here it is here. Here's some summary information about it. We could look at the attributes if we wanted. It's got a precipitation variable in there that has 3 axes, time, latitude, longitude. And you can see now that these, in terms of, it says it's a Dask array with a particular chunk size. And so we saw when I did ls at the command line that our original data files here are chunked by time. They've split up the 160 odd years of data into 25-year chunks. And then so we've decided here that we'd also like to chunk by time, because generally when we're reading in things with Xarray and we want it to read it in chunks instead of reading it in all in once, it's a good idea to use the same chunking as the netcdf files are chunked in. If we decided to chunk by latitude or longitude or something instead of time, then there would be an inconsistency between the way that the netcdf files were chunked and the way we're asking Xarray to chunk things, which wouldn't be useful. So we've said do it by the time axis. And if you look up on Xarray, basically uses a library called Dask underneath, and that's why this is called a Dask array here. And it's a library that we met in the first lesson on Tuesday when we were talking about kind of the core Python libraries that we tend to use. It's used for dealing with big data, for parallelizing things and all those kind of things. And Xarray is built on top of Dask, so you don't have to know the specifics of the Dask library. And instead you can just deal with your Xarray data array objects. So that's nice. But if you go to the Dask documentation, it says that I think the recommended chunk size is somewhere between like 10 and 1,000 megabytes. So we've picked 500 megabytes as a starting point as a chunk size for us here. So a good idea is to have a look at how that chunking has happened. So if we use our dset here and we get out our precipitation variable, kind of like we have before, and we have a look at the data, Jupyter notebooks are really smart and they can give us a nice pretty visualization of it. And so in total, it looks like we've got just over 60 gigabytes of data, which it's chunked into 499 megabyte chunks, which is good. We asked for 500 megabytes. And so there's 150 chunks all up. So 150 different NumPy and dimensional arrays. Cool. So let's say, so I was saying before that the task that I wanted to achieve here was to calculate the daily maximum precipitation over this 150 odd years of data. So let's define a variable called PRMax for the daily maximum precipitation. We want our dset, we want to pick out our precipitation variable, and then there's a max command that's attached to Xarray data arrays that we can use to calculate the maximum. And just like the mean function that we were using earlier to calculate our climatology, we can tell it what axis over which to calculate the maximum, so over the time axis. And like before, we wanted to keep the attributes, the file attributes once it's done. And so if we run that, it seems like it's happened instantly. It's like, oh, it's already calculated the maximum. And that's not actually true. What's actually happened is that, and we could look at PRMax here. It gives us another nice picture. The really nice thing about Xarray is that it does things what's called lazily. So when it looked like here that it read in the data, all it actually did was read in the metadata and show it to you. It didn't actually literally read in all the data values. And same here, it hasn't actually done the calculation yet of the precipitation maximum. It's just basically showing you what the output would look like if and when it does that calculation. And so it'll hold off on actually reading in the data and doing the calculation until the very last minute when you ask for the data because you want to plot it or something like that. And that avoids you getting like memory errors or things like that when you, let's say you open a data set and you actually only want the grid points over America, you don't want the whole world. If it read in the whole world data first, before you got a chance to say, oh, I'd actually just like to subset the grid points over America, that would be problematic. So this lazy loading behavior is really useful and stops you getting memory errors all the time. And so it hasn't actually calculated the maximum yet. It's just kind of telling me what it would look like if it were to do that. So I should actually go ahead now and make it do the calculation. And we should time it and see how long it takes. And so at the moment, we've set there's 150 chunks. And so it'll go through and it'll read in the data chunk by chunk instead of all at once. And hopefully then I won't get a memory error because I only have 17 gig of RAM on this computer and there's 60 odd gig of data. So hopefully by reading chunk by chunk, it'll be able to do this computation, even though technically I don't really have enough memory on my computer to do it. So in the notebook, I can set a timer. and I'm going to type compute. So I'm forcing X-array to stop being lazy and actually compute the maximum. And so that'll hopefully take a few minutes, but not any longer. So we'll let that run. And so you'll see in the notebooks a star there. And so the cell's not finished until that star is replaced with a number. And so, yeah, we'll set that running. While it's running, I guess a thing we need to think about is at the moment it's processing the data chunk by chunk, which is really nice, but it's only doing it on one core of my computer. And I've actually got 4 cores on this laptop. If I was on a supercomputing facility or something, I might have access to 100 cores or something like that. And so it'd be nice if we could distribute this task out to multiple cores on the computer instead of just using one. And we can use Dask to do that. And so I can set up a Dask client to manage this process. And so I can type from dask.distributed import client. And then I set a variable called client, which is the active client. And then I can actually view the client. So we're all set up now. So basically when, as soon as this first computation on one core is completed, I can set up a client and repeat the calculation on 4 cores and see if that gets us any performance improvement. So we'll just wait for that to run. And I'll give away the game here a little bit. A lot of the time, and what we'll find here, hopefully, once I run this, is that spreading this task across 4 cores will be slightly faster than doing it on one core, but not like 4 times faster, even though there are 4 cores. And sometimes that can seem a little counterintuitive, but there's some overhead involved in Dask having to set up and coordinate the process across separate cores. And so you can get in some situations where actually the overhead involved in spreading the task out across multiple cores takes longer than the actual task takes itself. And so you can end up actually having slower processing time when you run it in parallel than when you run it on one core. So that's something to keep in mind, that while Dask is very good at parallelizing things for you, oftentimes it's a bit of a trial and error to figure out whether the overheads associated with that particular task are so large that that it actually takes longer to coordinate than it does to do the process. And hopefully this task will finish soon. Has anyone got any questions quickly while we wait for? Yeah, so there's one in the chat there. Are you limited to just 4 cores? I am on this laptop because my laptop only has 4 cores. But if, like I said, if I was on a more powerful computer, or I logged into a high performance computing facility, I might have access to like 100 cores or even more. So a lot of people do that. Someone's asking, is there a progress bar or similar? There is, yeah, there's some commands where it'll show you a progress bar so you know that something's happening, as opposed to now where we're just kind of waiting for it to run. And so I'll actually do that when I set up the client. I'll show you the progress bar for the parallel processing. How do you kill a process in Jupyter? You can interrupt or restart the kernel at any time and it'll stop. So if this goes on much longer, I could stop it. Does it expand to hyperthread? I'm not sure. That maybe one of the other instructors knows the answer to that question. Or on Thursday next week, Kevin will be taking us through kind of Pangeo and big data in a bit more detail. So you might also get some kind of answers to those questions on next Thursday. Can you say more about how to choose the chunks? Yeah, I'd be interested actually next week hearing what Kevin and Scott and others have to say about picking the optimum chunk size. People I've talked to who do this a fair bit, it's still kind of, there's a little bit of trial and error. The golden rule is always to make sure that you're, unless you can help it, like make sure that your chunks align with the netcdf chunks. So in this case, the netcdf files are chunked along the time axis. So so we've chunked by time as well. And some people will actually re-chunk their data on disk, depending on what data processing they need to do, so that to make sure that they're getting those chunking consistencies. But yeah, other than trial and error of, I picked 500 megabytes because that was a good place to start. Yeah, I'm not sure if people have strategies besides trial and error for that kind of size selection. If you have more RAM than the 46 gig, would you still chunk it? No, not if it all fit in memory at once. Then there'd be no need. But yeah. So it's run now. It's taken 5 minutes, just over 5 minutes to run. So now if I start my Dask client, oh, that doesn't look good. It's worked when I did it last week. That's a shame because the taskbar is a really good. What's the error here? Cannot open name p open. That is disappointing. Someone else got that same error. I'm try and save. Yeah, so maybe what we'll do is we'll figure out the answer to this this problem, and at the beginning of the lesson next week, or actually during Kevin's big data lesson, we can give a bit of a demo on what happened. So yeah, I'm running it in parallel. Yeah, so that's what we might do. We'll wait for next week and do the Dask demo if we can figure out this error to get. Basically, it's really cool. It opens up a dashboard that shows what each core is doing and tells you what tasks are being done by what core when, and it's a nice little kind of visualization you can watch as the data's processing. But yeah, in the meantime, we'll have to live with these errors that unfortunately arise sometimes. So I might stop sharing my screen and kind of field any last minute questions on the big data stuff. Chat. Cool. So it looks like, yeah, Scott also ran into this error. Yeah, cool. But anyway, Dask is kind of your friend, and you'll find the nice thing is that a lot of the functions that you'll use, like the maximum, which we just calculated then, or mean, because they're built into Xarray, they're what's called Dask aware, which means that they know how to leverage Dask to do the things in chunks and all those kind of things. In the notes, there's some notes about what you do if you're trying to do something that's not Dask aware. So for instance, if you're using an obscure, I don't know, linear algebra or like interpolation routine from SciPy or something that isn't built into Xarray, there are things you can do to make that function Dask aware so that it can use the kind of the chunking and the parallelization and all the things. So there's things in the notes about that. But for most of the basic kind of calculations that you want to do, like calculating minimums and maximums and standard deviations and all those kind of things, they're already built into Xarray, and Dask is built into Xarray, so they're already Dask aware and ready to go. So yeah, that's a nice brief introduction to big data. And so we might leave the last challenge as homework because we're running a little over time today, but there's a few questions at the end of the large data lesson notes asking you to have a think about different strategies for big data and things like that. So have a work through them in your own time. And then, as I say, next Thursday we'll be kind of touching on big data again. So come on back then with any questions you've got relating to Dask and handling big data sets. But yeah, otherwise, has anyone got any questions before we wrap up for the day and reconvene next week?